Welcome! In this session, we'll be tackling an interesting problem from LeetCode, problem number 492, construct the rectangle. Together, we'll explore how to approach this challenge, analyze its requirements, and break it down step by step. Let's dive in. Imagine you are given an integer representing the area of a rectangle, and your goal is to determine the dimensions of that rectangle. Specifically, you need to find the length and width such that the product of these two dimensions equals the given area. Additionally, we want to ensure that the length is greater than or equal to the width, and that the difference between the two dimensions is as small as possible. In other words, the rectangle should be as close to a square in shape as possible. Once you calculate these dimensions, you return them as a list, L, W. For example, if the area is 4, one possible rectangle could have dimensions 4 and 1, but a better option would be 2 and 2, as it minimizes the difference between length and width. The input to the problem is the area, which is a positive integer, and the output is a list containing the length and width satisfying the conditions above. Let's consider the first example to make this clearer. If the input area is 4, we need to find all possible pairs of factors of 4. These pairs are 4, 1, and 2, 2. Among these, we look for the pair where the difference between the length and width is smallest. The pair 4, 1 has a difference of 3, while 2, 2 has a difference of 0. Since 2, 2 minimizes the difference, it is the best solution, and we return 2, 2 as the output. This example highlights how we prioritize minimizing the difference between length and width while ensuring their product equals the given area. Now, let's examine another example. If the area is 37, the only possible pairs of factors are 37, 1. This is because 37 is a prime number, which means it can only be factored as itself and 1. Since there are no other pairs to consider, the dimensions of the rectangle are simply 37, 1. In this case, the rectangle is long and narrow, but it satisfies the conditions of the problem, as the product of the dimensions equals the area, the length is greater than or equal to the width, and the difference between the two is minimized given the constraints. For a larger area, like 122122, the process is similar but with more factor pairs to evaluate. The possible pairs include 122122, 1, 61061, 2, and 427, 286, among others. We calculate the difference between the length and width for each pair and find that the pair, 427, 286, minimizes this difference. This pair forms a rectangle that is closer to being square-like compared to other options, while still satisfying all the conditions of the problem. Therefore, we return 427, 286 as the output. This demonstrates how the approach scales to handle larger inputs and more potential factor pairs. To wrap up, let's consider some edge cases. For the smallest possible area of 1, the only rectangle you can form is a square with dimensions 1, 1. This is because the only factor pair of 1 is 1, 1. For a prime number like 29, the only factors are 29 and 1, so the output would be 29, 1. Finally, for a very large area, such as 10 million, it's important that the solution remains efficient, as the number of potential factor pairs to evaluate increases significantly. The algorithm should handle these cases without performance issues, ensuring correctness and speed even for the largest inputs within the constraints. To solve the construct the rectangle problem, we can start by considering the brute force approach. The idea here is straightforward. We iterate through all possible dimensions of the rectangle, specifically testing each width from 1 up to the given area. For each width, we calculate the corresponding length by dividing the area by the width. If the product of width and length equals the given area, and the length is greater than or equal to the width, we consider it as a valid solution. While this approach guarantees that we find a solution, it has a significant drawback: it's computationally expensive. Because we need to check every possible width up to the area, the time complexity is O, area. This means that for large values of the area, the number of iterations can grow excessively, making this approach inefficient for larger inputs. Next, we can explore a more optimized way to find the dimensions while reducing the computational overhead. By focusing on efficiency, we can use an optimized approach based on a key observation: the dimensions of the rectangle are factors of the given area. Instead of iterating through all integers, we can restrict our search to numbers up to the square root of the area. This is because any factor greater than the square root will have a corresponding factor that is smaller than the square root. To implement this, we start with the largest possible width, which is the square root of the area, and check if it divides the area evenly. If it does, we compute the corresponding length as area divided by width. Since we are starting from the largest possible width and moving downward, the first valid pair we find will automatically satisfy the condition that the length is greater than or equal to the width. This change reduces the number of iterations to O, sqrt, area, making it significantly more efficient for larger values of the area. The key realization here is that by leveraging the symmetry of factors around the square root, we can drastically minimize computation while maintaining correctness. When comparing the two approaches, there are clear trade-offs to consider. The brute force method is advantageous in its simplicity, it's easy to understand and implement. However, it becomes impractical for large values of the area due to its area, time complexity. On the other hand, the optimized approach is much more efficient, with a time complexity of sqrt, area, which makes it scalable for larger inputs. The trade-off is that it is slightly more complex to implement. It requires iterating in reverse from the square root and checking for factors, which involves a bit more mathematical reasoning. Despite this, the optimized solution is the better choice as it strikes a balance between performance and implementation complexity. Its efficiency and direct use of mathematical properties make it ideal for solving this problem effectively. To solve this problem, we need to determine all possible pairs of dimensions, width and length, of a rectangle that result in a given area. These dimensions must be integers, and we aim to avoid redundant calculations. For example, the pair, width, length, should be treated as identical to length, width. To do this efficiently, we can use some mathematical insights. First, we start by understanding that for any valid pair, the product of width and length must equal the given area. Next, since the two dimensions are symmetric around the square root of the area, there's no need to check values greater than the square root. This symmetry allows us to reduce the range of our search, improving efficiency, and ensures we don't count duplicate pairs. The goal is to calculate these pairs methodically while minimizing unnecessary operations. Now that we understand the problem, we can break the solution into clear steps. We begin by iterating through all possible integer widths from 1 to the square root of the area. For each width, we check if it divides the area evenly using the modulo operator. If the condition area %width equals 0 is satisfied, it means that width is a valid dimension. We can then calculate the corresponding length using integer division, length equals area/width. Together, these two numbers form a valid pair, which we store. By limiting our range to the square root of the area and leveraging the modulo operation to filter out invalid widths, we significantly reduce the number of computations required. Once we've processed all potential widths, we return the list of valid pairs. This approach is both efficient and avoids counting duplicate pairs, thanks to the mathematical symmetry between width and length. To implement this algorithm, we rely on two key data structures and mathematical operations. The pairs of dimensions are stored as tuples in a list, making the solution simple and lightweight. Tuples are ideal here because they are immutable and have a fixed size, providing a clean way to represent each pair. Additionally, we use basic mathematical operations such as modulo for divisibility checks and integer division to compute lengths. Together, these operations ensure precision and avoid complications like floating point errors. In terms of time complexity, the algorithm is highly efficient, running in sqrt, area, because we only iterate up to the square root of the area. Space complexity is minimal and scales with the number of valid pairs, which is much smaller than the area itself. Here's a concise pseudocode implementation: iterate through widths from 1 to sqrt, area, check divisibility, compute the corresponding length, and store the pair. This straightforward approach ensures correctness without sacrificing performance. When designing an algorithm, it's important to consider edge cases. For example, if the area is 1, the only possible pair is 1, 1. For a prime area, such as 7, the only valid pairs are 1, 7, and 7, 1, since no other integers divide the area evenly. If the area is a perfect square, like 16, the pair 4, 4 must only be included once, since it doesn't make sense to duplicate symmetric pairs. For very large areas, the efficiency of the algorithm becomes critical. By limiting the search to integers up to the square root of the area, we ensure that even large inputs are processed quickly. To illustrate, consider an area of 12. We start with a width of 1, which gives a length of 12. This pair, 1, 12, is valid and added to the list. Next, we check with 2, which divides 12 evenly, yielding the pair, 2, 6. Continuing with the same example, we increment the width to 3. Since 12 is divisible by 3, we calculate the corresponding length as 12 divided by 3, which equals 4. This gives us another valid pair, 3, 4. At this point, we stop because the next potential width, 4, exceeds the square root of 12, which is approximately 3.46. The algorithm ensures that all valid pairs are found efficiently and without duplication. The final output for an area of 12 is 1, 12, 2, 6, 3, 4. This demonstrates how the algorithm handles symmetry, reduces computations, and produces the correct result in a structured and logical manner. By limiting the search range and carefully checking each width, we ensure that the solution is both optimal and robust for a variety of inputs. The provided code solves the problem of finding dimensions for a rectangle that satisfies a given area, ensuring that the rectangle's width is less than or equal to its length. The algorithm starts by identifying the largest possible width less than or equal to the square root of the area, as this minimizes the difference between the width and the length. Using a while loop, the code iterates to find the largest divisor of the area that can be used as the width. Once a valid width is found, the length is calculated as the quotient of the area divided by the width. The solution is efficient because it only considers potential widths up to the square root of the area, ensuring that the algorithm runs in sqrt, area, time. The function finally returns the dimensions, length, width, as the output. This is the Java implementation of LeetCode problem number 492, construct the rectangle. The logic mirrors the Python implementation, starting with the largest possible width less than or equal to the square root of the area and decrementing until a divisor is found. Java-specific differences include explicit type declarations, usage of math.sqrt, and returning an array for the dimensions. The main method demonstrates usage with an example. To solve this problem, we start by finding the largest possible width that is less than or equal to the square root of the area. In this first example, the area is 4, and the square root of 4 is 2. So we initialize the width to 2. Next, we check if this width divides the area evenly by verifying if the remainder of 4 divided by 2 is 0. Since 4 divided by 2 equals 2 with no remainder, we know that 2 is a valid width. Once we have a valid width, we calculate the corresponding length by dividing the area by the width. Here, 4 divided by 2 gives us a length of 2. Therefore, the dimensions of the rectangle are 2 by 2, and the output is 2, 2. Now, in this example, the area is 37. Again, we start by calculating the largest possible width that is less than or equal to the square root of 37. The square root of 37 is approximately 6.08, so we initialize the width to the integer part, which is 6. We then check if 37 is divisible by 6, but it is not. This means we need to decrement the width and check again. We continue this process, decrementing to 5, then 4, 3, and 2, but none of these widths divide 37 evenly. Finally, when the width reaches 1, we find that 37 is divisible by 1. With a valid width of 1, we calculate the length as 37 divided by 1, which equals 37. Thus, the dimensions of the rectangle are 37 by 1, and the output is 37, 1. Here, the area is 12. To find the dimensions, we start by calculating the largest possible width less than or equal to the square root of 12. The square root of 12 is approximately 3.46, so we initialize the width to the integer part, which is 3. Next, we check if 12 is divisible by 3. Since 12 divided by 3 equals 4 with no remainder, 3 is a valid width. Once we have this valid width, we calculate the length by dividing the area by the width. Here, 12 divided by 3 gives us a length of 4. Therefore, the dimensions of the rectangle are 4 by 3, and the output is 4, 3. To analyze the time complexity of our solution to problem number 492, we begin by looking at the initialization of the width variable. Here, we calculate the integer square root of the given area using the expression int area 0.5. This operation is essentially a mathematical computation that does not depend on the size of the input and can be performed in constant time, or O1. Next, we move to the iterative search for a divisor within the while loop. The loop begins with width starting at the square root of area and decrements until it finds the largest divisor less than or equal to the square root. In the worst-case scenario, the number of iterations in the loop is proportional to the square root of the area, as it may need to check all numbers down to 1. Since each iteration involves a simple modulus operation, which is also constant time, the overall time complexity of the loop is O(sqrt) area. Once the loop terminates, the value of length is calculated as area//width. This division is performed only once and is a constant time operation with a complexity of O(1). Now, if we combine all the steps of this solution, the while loop dominates the overall time complexity, resulting in an overall complexity of O(sqrt) area. Shifting our focus to space complexity, this solution is highly efficient in its use of memory. It relies on just two integer variables, width and length, to store intermediate values. Since these variables occupy a constant amount of space, the space complexity is O(1). Moreover, there are no additional data structures, such as arrays or maps, used in this approach that would scale with the input size. Thus, we can confidently conclude that the space complexity remains constant. Let's compare this optimized solution to a brute force approach. A naive method would involve iterating through all possible values of width from 1 to area, checking if each is a divisor by performing the modulus operation. For every valid divisor, the corresponding length would then be calculated as area//width. The time complexity of this brute force method is area, because it examines every integer up to area. In contrast, the optimized solution drastically reduces this effort by limiting the search space to integers from the square root of area down to 1. This is based on the mathematical property that any divisor pair of a number will have one value less than or equal to its square root. By narrowing the range of numbers to check, the time complexity improves to O(sqrt) area, making the optimized solution significantly more efficient for large input values. Finally, let's analyze the time complexity across different scenarios. In the best case, the very first value of width tested, which is the square root of area, is a divisor. Here, the loop terminates immediately, resulting in a time complexity of O(1). On average, the loop will iterate through roughly half of the possible values within the range from sqrt area to 1, leading to a time complexity of approximately O(sqrt) area. The worst-case scenario occurs when area is a prime number, meaning the loop must check every integer down to 1 before it finds a valid divisor. Even in this case, the complexity remains O(sqrt) area. This efficiency is rooted in the mathematical property of divisors. For any number n, if a is a divisor, then b equals n/a is also a divisor, and one of these values must be less than or equal to the square root of n. By leveraging this property, the algorithm ensures all possible divisors are considered within the reduced range, keeping the time complexity proportional to sqrt area. When tackling this problem, there are a few common mistakes to watch out for. First, incomplete edge case handling can trip you up. For example, you need to consider scenarios like very small or very large inputs, and if the problem allows, negative values or duplicates. If the task involves dimensions, remember to account for cases where the width and length are equal. Another frequent issue is using an inefficient brute force approach without leveraging mathematical properties, which can lead to performance problems, especially with large constraints like 10 to the power of 5 or 10 to the power of 6. Similarly, incorrect bounds on loops can waste computation time. For instance, if you're checking divisors for an area of 36, iterating all the way to 36 is redundant when you can stop at the square root, which is 6. Mismanaging integer division is another pitfall. In Python, for example, mistakenly using / instead of // can result in floating point values, which might break your logic. Lastly, overlooking problem-specific constraints, such as the maximum difference between dimensions, can lead to invalid outputs. These are all critical areas to double-check in your approach. Now, let's talk about insights that can help in interviews. Recognizing patterns is key. Many rectangle or area-related problems revolve around mathematical relationships like divisors, square roots, or symmetry. Spotting these early can help simplify your solution. Once you've clarified a brute force approach, interviewers often expect you to optimize it, such as by reducing loops to run only up to the square root of a number or by leveraging sorted divisors. Another useful skill is generating test cases. Be prepared to validate your solution with edge cases such as the smallest and largest possible inputs, or scenarios where the dimensions are equal. It's also important to explain trade-offs if there are multiple approaches. For example, a brute force method might be easier to implement but slower, while an optimized method may require more complex logic. Understanding and communicating these trade-offs can leave a strong impression. Finally, related problems like LeetCode 172 for factorial trailing zeros or LeetCode 867 for matrix transposition feature similar mathematical reasoning, so practicing these can build transferable skills. Let's explore some alternative approaches for solving this problem. The first is a brute force approach, where you iterate through all possible widths and calculate the corresponding length to check if their product matches the given area. While this method is simple to implement, it's inefficient for large inputs due to its linear complexity, O(n). A more optimized approach involves limiting your iteration to the square root of the area. Here, you find divisors up to sqrt, area, and for each divisor, calculate the complementary dimension. This significantly reduces the number of iterations, achieving a complexity of O(sqrt)(n), though it requires a solid understanding of divisor properties. Lastly, if the problem involves multiple queries, you could pre-compute divisors for common values. Once pre-processed, each query can be handled in O(n)(0.5) time, making it very efficient. However, this approach requires additional memory to store the divisors. Each of these methods has its trade-offs, so the best choice depends on the specific constraints and requirements of the problem. Great job! To summarize, we solved the construct the rectangle problem by leveraging mathematical properties to optimize our solution. Remember, efficient problem solving involves both understanding the theory and practicing it. Thanks for tuning in, and be sure to check out more coding solutions on our channel. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!